Okay, I'm going to go ahead and get started here. We'll probably be interrupted at some point while I'm encoding last hour's video, so it's not there. All right, I'm going to go through here a little bit the last book that I put up there, which is the one called Embedded Microcontrollers that there, and just kind of talk a little bit, go a little further into that book there. One of the things that's in that textbook early on is this big table right here. That there, and what page is this on here? That's figure 1 to page 8 there. And this table basically talks about how the memory is located within the device. And this isn't real important that you know this table, it's just that it's there. And here, as we look at this right here, go through that there. The second part of this here gets into, for example, here, and we'll talk a little bit in more detail, that P1, which is port 1, is actually stored in a register within the microprocessor, and it's at location 90. This particular microprocessor uses what I call memory mapped I/O. That's there. And when I say memory mapped I/O, it means that I talk to memory the same as if I'm talking to I/O or vice versa. If I want to talk to a memory or a output device or a port, I just write to its location. In this particular location, P1 happens to have address 90. And I'm going to just write a short little assembly language program here where I just simply set a bit on port 90, which happens to be an LED, and clear it continuously that there. So that there. Now you don't have to memorize this table, and the reason you don't have to memorize this table is that Silicon Labs has done something very, very nice for people that use this in the fact that where is it? ASM1. Project window is that they created a file that when you and I'll go through the process of creating a new project here, but there's a file that they generate for you, and they include it in your project when you create a new project that contains in it all these locations, these special function registers. The 8051 lives on special function registers. A special function register is exactly what it is. It's a location in memory that you write to it that does a function. So, for example, the port 1 is defined, and I don't think I can do, I can do it this way here. If I come down here, you see right here is port 1 right there. And that's the same one I showed you in that table earlier. And this simply defines port 1 at address 90. So that means that when we write our code, we can use P1 and we don't have to use 90. We don't have to remember that port 1 happens to be at memory location 90. The only time this becomes a problem, and it does become a problem, is when you use a different microcontroller. You know, a new one comes out, and they add new special function registers that are not in the file. Or if you happen to be using another microprocessor other than, say, Silicon Labs, and you're using the same compiler. Silicon Labs provides this for pretty much all their chips, but Atmel doesn't. In all these microprocessors, we're using the Silicon Labs IDE, but when we compile this, Silicon Labs does not generate a compiler. They do not have a compiler. They're using a compiler called the Kyle compiler. It's a company that sells these compilers. They're very expensive if you buy the full-blown one, and we're talking 10,000 RM for a single license. That's there. For student use, for what we're using in this class, they give us a free license. That's there. So, you know, we're not running pirated software here. We're running legit software, but they provide a license for us to use in this class there. So, but they provide that, and I'm just going to kind of go through a little bit of the instruction set here, but just keep in mind that anytime we want to access a port, P2 happens to be at A0, that there, and it has the term active at the end of it, which means that port 1, port 2, in this particular case right here, is not active because this particular chip family doesn't have a port 2 right there. So if we try to use port 2, we'll get an error because there is no port 2 on this particular chip. And I know I passed this around several times, or at least once, but as you recall, this particular chip only has 20 pins. So we only have port 0 and port 1. There is no port 2 on there. So as you look at this table here, they use a generic table for all their 8051 families, but they make ports active or inactive depending on what particular device. So in this particular case, we can't write to port 2. We can only write to port 1, 0, and 1. Those are the only 2 ports we've got available right there. So as we go through and look at this right here, I'm going to close this file up. I wrote a very, I shouldn't say I wrote, I took one of their sample programs and I modified it to run on this chip. They did not give me an assembly language sample program, so I took one from another chip and I just modified it to work on this chip out there. And this is the way that a typical assembly language program is going to have to look for this processor right here. The first thing we're going to basically do is this is a assembler directive that just simply says no modification. It's a 51 code. So this is telling the compiler that we're writing 8051 code, and we're not doing any modification to it right there. And this includes that file that I just showed you a few minutes ago that has all the definitions. So as we do labs in this course, we will include this file out there. Now, if we're writing C code, which we're going to be moving to C at some point, we will then use the C version of this right there. All right, here I simply said that the green LED, actually in this particular case, it's not green or yellow, it's just an LED, is at port 1.0. So if you look at this particular board, I can see that I got an LED at port 1.1 and one at port 0 or 1.0. So I'm using the one at 1.0. Now I can put another line in here, and I will here in a few minutes, say red LED is at that port, and I can toggle the opposite of each other right there. So I can talk both ports there. Now this is something that you probably wouldn't have guessed on your own, but we have to tell this that at location 0, we want to jump to main. Our main, in assembly language or C, our main program we're just going to call main. That's our entry point to our program. But in assembly language, we have to set the reset vector that when the processor is turned on, it always goes to location 0. That's the reset location right there. And what we want to have happen is we want this to jump to location main. This is a long jump. And the command for long jump is ljump. So in the code segment at location 0, we're going to just put one instruction that says jump to main. And that's where we're going to write our code right there. And this is a format, and I'll make this available to you there. Now blink just simply is we're setting up here a segment of code right there, and that's the name of our program. It's code, and it's just a specify what's register bank. We're just going to stick in register bank 0 because of the way this processor, we haven't got into it, allows us to have multiple register or code segments because the 8051 uses what they call a banking mechanism. So we have to tell what bank our code is going to be, and we're just going to use bank 0 right there. Now bank just happens to be a block of code right there. So we're just going, our programs are going to be small for this point, so we're just going to set them at, well, put everything in location 0. We're not going to write anything bigger than 2K, so we can stay in one bank. We don't have to fool with adjusting bank. Some of the older processors didn't have that. The next two segments right here, this main starts the program. It's a label. We write the word main. We follow it with a colon, and the assembly editor will put that as blank, as black. That's just a label. And remember, our first line of code back there was long jump to main, so it's going to jump to this location right there. So this is the start of our code. Now, this is very similar to the beginning of that C program I showed you last week here, but instead of saying that there, we just use the move instruction. Now, what those are is we're moving into our watchdog timer control register. We're just moving DE and AD to turn it off. If you go back and look at that one that I did last week, which was in C, you'll see the C equivalent to that there. The watchdog TNC, that they're along with the crossbar, basically there are registers that are defined in that include file. And we'll just include these at the beginning of every piece of code that we want. Now here we're only using one input, and I didn't change that. That should be location set P1.0 there as a digital output in push-pull mode. Now if I want to say use 0 and 1, I would just simply change that to a 3. And I will do that in a few minutes in order to toggle two of that there. So this right here is a command. All this does is turn off the LED when we start running our program. It just clears that bit right there. And then we just have a simple delay loop, and all this is a nested for next loop. I think everybody's had a course in C, right? So all we're doing is we've got a jump to loop 0 where we're decrement and jump of 0 back to here. So we're moving 3, 0, 0, and we're just creating this series of infinite loops is what we're doing, or these loops there. That all we're doing is we're jumping from each one of those loops there. So we move into register 7, the number 3 hex, and we move into register 6, 0, and register 5, 0, and then we do a decrement of not 0 back to the same location. We just hang that there, and then we decrement 6, and if it's not 0, we jump back to loop 0. If it's 0, then we're going to jump down to the next one and decrement 7, and we just keep repeating. This is a series of 4 next loops. All this is we're just decrementing and jumping, if not 0, to the location. This just simply means stay in the same location. Just keep spinning. All we're doing is killing time. That's all those 3, 4, 5 lines are doing. We're killing time. As you recall, the one that I did in C, I used the timer and the interrupt to do that. Here we're just putting a 4 next loop, and I can make this loop longer by just changing that 3 to a 4 or 5 or shorter. And that there, and the interior of that there, and you could go through a lot of calculations. We're not going to do that now. Maybe later we might have time where we go through and see how many seconds of delay we're getting there. Because each instruction, we're running at a 24.5 megahertz clock. How many clock cycles does it take to do each one of these instructions? And then we can determine how long this delay is. Right now, all I'm concerned about is we're just delaying long enough where we can see the lights go blinking, right there. And then the last command is all we do is complement the green LED. If it's a 1, we make it a 0. If it's a 0, we make it a 1. Right there. And then we go through here and we jump back to the start of our code right there, our loop. And that's our infinite loop right there. We stay in this loop forever. right there. So we started the loop by moving 3 into R7, then we move 0, 0 in R6, then 0, 0 in R5. We just circle, 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 circle until R5 is 0. Then we decrement R6 to jump back and restart the inner loop again. And we go through that FF times, because when we decrement it, the first time we put 0, 0 in it, we decrement it, it's now FF. Not there. So it's going to go 255 times through that inner loop right there. Then 255 times around the outer loop, and it's going to go 3 times around the upper loop right there. So it's going to go through that inner loop 3 times 255, 256 times 256. So it's going to be going through this loop quite a few times. If you put something other than 0, 0, then it's going to shorten the time. 0, 0 is the maximum number you can put, because when you subtract 1 from it, that becomes 255. That's why that's the maximum number. If you put up there, it doesn't make sense to put 0, 0 and say that's the maximum. But the decrement and jump not 0 does the decrement first, checks the 0 flag, and if the 0 flag is set, then it does the jump, or doesn't do the jump. There. So and it will go from the 0 flag will be set when it goes from 0, 1 to 0, not when you go from 0, 0 to FF. So whenever you subtract 1 from an 8-bit number, you end up with FF. There. And this is the whole code, and then the last statement you have is the end. So this is the format that the assembly language code is going to look like, right there. And I can go through and I can compile this right here. And I'm just going to do a compile. Now, something about this particular processor is under the options. Let me disconnect this here. Disconnect it here. Under the connection options, you'll run into this here. You'll have to set this to C2 for this particular board, not JTAG, right there. Okay, so we go ahead and connect it. We download our code to it, right there. And at this point, we can start running this right here. Now, our debug window, or our view windows, we can look at our registers, our ports, right there. We can then look at our our registers, right here, and right there, debug, and we want to view debug windows. We also want to look at our code memory. We want to, excuse me here. Right there. Okay, and what I want to see here is I want to be able to get my project at their view. I want to see. Okay. All right. What we've got here is we can go through it in single step through our code, and what we can see here is you can see as we clear that LED. Now, actually, remember that when we write a 0 to it, we actually turn it on. So actually, initialize it. This actually means on right there. Right there. So I just turned on the LED, and it's a red LED. It's not a green LED. Again, I got there. And I can run this program, and it'll just keep blinking. Everyone can see that it blinks. I can stop this here. Now, again, I'm going to put a stop right here, a breakpoint right here, and just run to this point right here. Right there. And you'll notice here that as I single step through here, R7 is now has 03 in there. I can see what's happening at the registers right there. Then I'm going to move 00 into R6. which is I've done there. And I move 0, 0 into R5, right there, which is what they had before. Now when I jump that, notice that R5 contains FF, right there. And each time I hit this button, it goes down by 1, and I'll have to hit that button 256 times before it'll go down, before it goes to the next command. It's going to stay in that instruction every time I hit this button, right there. Now I'm going to not do that. I'm going to do this step next, where it's going through, and it's, as you see, it's counting down here, right there. And it's going through, and it's stepping through the program one instruction at a time, and I can watch the registers change. And it's slow enough that I can see things changing. When that gets to 0, 0, it will go down to the next instruction. When it goes to the next instruction, you'll see that R6 will go to FF. And then R5 will start counting down again. So you can see what's happening within the loops right here. That there. And I know it's painful to watch, but it really helps understand what's happening within the processor to go through the, watch these steps up there. All right, see now we're going to go, and notice that we start the process over again, but R6 now has gone to FF. Now I'm going to stop this and tell it to just run, right there. And notice that it comes back here. Now my LED is off because I went through it and I complemented it. And I'm back here ready to start the process again. R7 is 0, 0, because we've got to this command right here. So we jump back to loop 1, loop 2, because we dropped out of this one here, right there. Now I can go ahead and I can put a breakpoint here. Excuse me, right here. Why are we not setting a breakpoint right here? Okay, there we go. Right there. So now I run through here, and notice that it's now R3. These two are 0. I step through this again. Now it's 2. I run this again. You can see I go through that each one, and this time it's going to be a 0. If I single step through this, I'm back to the top there. Right there. So I can single step through this code and see what's happening. I see what's happening in each of the registers. I also see that port 0, or port 1 is FA, which I'm not sure what there. The LED is on, which tells me right there. If I run through, let me clear this breakpoint right here. Oh, I didn't turn. Let's put the breakpoint here. Right there. If I single step through here, notice that that goes to FB. That means I've turned that port. I turned it, wrote a 1 to it. If I go through it and run it again, it goes to FA. It means that I wrote a 0 to it, and the LED is on. Right there. So I can very easily go through that. Now I can go through it and do both ports in flash lights up there. I'm going to go through and I'm going to put this as 3 because I want to write a 1 to both ports 1 and 0. And I'm going to call, I'm going to call this red LED, even though they're both red. I'm just calling them red LED. Equate port 1.1 right there. And what I'm going to come down here is I'm going to set red LED. Right there. So now I'm going to turn off the red LED. Now remember, these are reversed. Right there. And then down here, I do the same thing right there. Oh, and what did I do wrong here? Say a complement. In other words, if it's a 1 or 0, it's a not function, complement. In other words, it changes it from 1 to 0 or 0 to 1. And this has got an error view output window. It doesn't like my command. Set. Oh, it doesn't like set. It does not like set. I thought set was the right command. Well, we'll just do it this way. This is kind of the awkward way of doing it, but no error, so no. And now you can see that I've got them flashing opposite of each other right there. Right there. So yeah, the set command doesn't work with this particular assembler for some reason. Right there. But you can see how we can look at the hardware and we can write the code for this particular processor. I know with the 8086 you didn't do any of this right there. Now, again, we can still do the same thing you did with the 8086. We can still write a simple little code. Let me just save this right here. And let me just kind of go through here. And I can write any type of code I want here. And I'm just going to copy this right here. And the reason I want to copy it is because I'm going to use this as a shell. Project, close project. Right there, save project. And I'm just going to create a new project from scratch right here. And I'm just going to do something very simple like the lab instruction that there where we just add 3 numbers and we see what's going on right there. So project right there, and we're going to do a new project. And typically the way we do a new project, we specify the device we want right here. We're going to say that it's going to be an assembly language program in this particular case, and we're going to call this ASM2 right there, just for sake of argument right there. Right there. And view. And project window. You see it's added that to the project right there. So now we're going to just go ahead and add a new ASM source file right there. We're going to add it to the project, add it to the build, because we can hit build, and I'm just going to call it ASM2 right there. And what we're given is an empty file, and I'm just going to paste what I copied before, and I'm just going to delete all this right here. Because in this particular case, actually I'm going to delete up to this right here. So this is the shell on which most of our programs are going to start with right there. We'll start with this shell right there. I could leave this here because I may want to do something with the LEDs if I want to. Right there. Right there. So our code is actually going to go right here. This is where, and I'm going to put a comment in here, semicolon, insert your code here, right there. So this is where your code would go if we're going to write an assembly language program right there. And I'm just going to write a very simple assembly language program where I write to the accumulator or A, and I'm just going to add 3 numbers, very similar to the example that we did earlier right there. So let's just simply say move into A the number 55 hex right there. So that's all we're doing, and we're just going to add to A the number 21 hex. We're going to add to A the number 12 hex. And that's all we're going to do that there. You know, let's just do a long jump back to main right there. So that's our code, and we'll just compile it, see whether I did it right. All right, everything went fine. I compiled it, so I can now download it to my processor. Oh, I didn't link it there. Okay, this is the restricted version, but that there. Actually, there's a process to get the full version, but we're okay. We've got that there. So, and I have to disconnect it. Oh, options, connection options. We have to set that back to C2. Now we connect it, and then we just download our code. Now I don't want to just run this code because it's not going to do anything. It's just, I'm not lighting LEDs. It's not going to do anything at all. So at this particular point, what I want to do here is I want to view the debug window, and I want to look at the registers right there, because I'm just using the registers there, or not the registers, excuse me. I want to use the 8051 right here. So we got our debug windows, and the register the only register I'm using is the accumulator right there. A is the accumulator. So I'm going to, if I go through and I step through our code, first off, I'm doing stuff with the watchdog timer. Well, right there. Now, as I exercise the next instruction, notice that 55 moved into the accumulator right there. Also notice that my program counter is sitting there at 80B. The assembler put this at 800. Is where I put it at there. So I step through the next one. I add 21 to that. So now I've got 76. I add 12 to that. I've got 88 right there. And then I jump back to main right there. See? And I could do this all day long, and I'm just going to see the same numbers flash back and forth up there. It's just running my code one instruction at a time is what that's doing. And this is what you did with the 8086, right? And probably bored you to death right there. But we could do the same thing here. The only difference is it only works if we have this. You know, you see, and I can turn right around and I can do things like here. Let's stop this here. Let's Control Z. I can go through here and I can clear red LED, clear green LED right there. I can just simply complement green LED right here, and I can come down here at the bottom here, and before my jump, complement red LED, complement green, and the assembler is not case sensitive right there. And I keep touching the LED. So now I just reassemble it, download it, and now as I go through my code, I'm seeing that my LEDs are, you know, one's on, one's off. I turn them on and off. I move 55 into the accumulator. I added 21 to the accumulator. I added 12 to it. I turn off all the LED, turn on one LED. I flipped it back on, and I just jump right back to main, right there. So I can write my LEDs. I can add my numbers. So you know, I can do all that, and there. If I took this processor off, though, or if I took this board out, I can't simulate this code, though. This particular compiler does not come with a simulator. So you have to have the board to run this. I got 2 of them in yesterday, yesterday I got 2 of them in. I'm expecting the other 16 in sometime later this week, and then we'll start doing labs out there. So, there. But that's my little demo on how we would do assembly language code out there. Again, this portion right here, this is where you'll be writing your assembly language code is right there. Everything else will be given to you right there, simply because that's the overhead out there. And quite honest, I'll be honest that I don't, whenever I use a new compiler, a new board, whatever, I just go through and find an example to steal the prep work that's there. Sometimes I have to go through and figure it out on my own, but most of the time I usually just, find an example and I make it work. And that's what I did yesterday for about half an hour. I found an example, I made it work, twisted around, and made the adjustments to be used with this processor right there. So, okay, let me jump ahead up there. Here, let me, right there. So going back to this particular book, right there, we see that we've got a lot of these addresses given for there. This again is we're going to be working probably in the lab sections. We'll talk a little bit about that there, and there we've got some instructions here to moving. One of the things that we look at here is that we've got multiple addressing modes, and this makes our assembly language very, very interesting in the fact that we've got these multiple addressing modes. If we have a number, that's going to point to a memory location right there. So move A, comma 62 means that it's going to look at the address location 62 and move that into the accumulator. And one of the things that is a little confusing is when you look at the 8051 Windows, it says the register ACC, and in the assembler we use A. They're the same. ACC means the accumulator. Registers B and the others at there. So when we look at something like this right here where it says move A, if it just has a number, and we almost always use these numbers in hex, which is why we spend a lot of time talking about hex numbers. We're looking at address. When we use it with the number sign in front, right there, we're looking at the actual number 62. Going back to that code that I had, I said move into A, comma, number sign 55, I think. Didn't I start with 55? So I actually moved the number 55 there into the accumulator. So that's what that number sign is, means that you're actually moving that number. So if we have the ampersand, means that that register holds the address of the number. So we've got 3 different ways. We've got a direct addressing, immediate data, and indirect. Why would we use something like indirect? If we're processing an array where we have a bunch of data stored in memory, we would increment the register and then look at and do the next add. If we want to add a bunch of numbers, that's there. So again, we would set that up there. So we can write some code where we use the indirect, where we load into the register the starting address of our array, and we go through and we add up 10 numbers right there. And we'll be doing some examples like that. Now, bit addressable means that we're going to, right there, this is what, here, and this gets a little bit confusing. This is really where that program comes in handy, or that include file comes in here. Remember, I did a clear green LED out there, but green LED I set equal to the equate command to P1.0 right there. What the assembler actually does is it converts that to clear and whatever the bit address of that. Because remember, if we go back to this table right here. This is where this table gets interesting. Right here. And if I find it again here. Right here, here's 90, right here. And the bit address for port 1.0 is 90. This is port 1.191. In my code, I use P1.0 because that tells me port 1 bit 0. But if I didn't have that include file, I would have to use 90 and 91 right there instead of red LED and green LED. So you can see where that include file makes our code much easier to work with. Out there. Otherwise, you're going back to this table and say, I want to use port 1 bit 3. Well, port 1 bit 3 happens to be 0, 1, 2, 3, bit location 93. So then I have to clear 93. What does clear 93 mean if you don't know this processor? Like you know, driving your car. Most people know the inside of their car and how it handles, real well, right? How well do you know this processor? You don't know this processor. We're talking a whole new language here with this thing. So P1.3 makes a lot more sense than clear 93. So that's where we're getting into as we write our code, but it goes back to this table. This table comes from the data sheet for this processor. And the reason I'm harping on this is if you deal with a brand new processor you've never seen before, it just came out, you may not have that file there. You may have to go through and get back to where these numbers came from. That's there. And I've had these files be wrong. I've actually gotten, bought a compiler from, or bought a chip or a development board from a company like Silicon Labs or Atmel, and I download the software, or they give it to me on DVD with the development system on it. I go through it and I'm debugging my code, and it won't work. And I go through their include file and I compare it to the data sheet, and I find that somebody did like I did. They copied from a previous version and didn't correct everything. And they released that. Now version 2 comes out 3 weeks later with it corrected. By that time I'm 3 weeks behind schedule, and my boss is screaming at me. Not there. Not that that's ever happened. Well, it's only happened twice. It has happened. Trust me. That's there. Because you pick a new processor and you think that it's going to work great, and so this table actually, now this table's set pretty much in stone for any 8051 chip. Right there. It's only when we get to the newer, more advanced chips. The chips we're using is just using a subset of the 8051 because it's a very small chip. Therefore, we won't have that problem. Right there. But if you're using something brand new, then it's going to be a problem right there. So, I didn't want to do that. Okay, going back to right here, up there, bit addressable RAM. Now, we've got some right there. This here is, again, kind of that same thing where this is multiple ways of doing the same thing. This command right here, clear 78, clears bit 78, which goes back to bit 78 is bit 78 is location 0 in bit address 2F. That's not a port or anything. So it's this bit here. It's bit 0 on memory location 2F is what that is. So and we could easily do that just as well with bit 90 right there. Here we're moving into a the address 2F, that there, and we're ANDing the location, ANDing that with this bit right here, and then we're moving A back to this location right there. So that there, the other option is to use 2F.0, which is very similar to the port 1.0 that I use right there. So register banks, these are used, there's 32 locations. We're not going to dwell too much on that, right, on register banks right now. They are used for a number of purposes. We will have to get into them later, right there. Special function registers, that's, I did set, it's supposed to be set bit. That's why it didn't work right. Remember I tried set and it barked at me, that there, I forgot the B. That's there. So, as I said, I don't use assembler very often, that there. So, it's set B. Special function registers, they're configured as part of the on-chip RAM. So, whenever we want to read or write a port, we're reading a special function register right there. So we have set bit at there. If I go back to the code that I wrote a few minutes ago, right there. I can do a set bit here. Right there. See, that's the one I screwed up that there. And now as I go through and I single step through this right here, I clear the red one. When I clear the red one, that turns it on. So I turn on that one. And if I step this one, that turns it off. It's already on. Right there. So I flip those on and off. So the set bit is the one that I messed up that there. So okay, going back right there. That's our set bits. The program status registers. These are this is a special register that tells what's happening within the last instruction. Uh-oh. Starting to lose everybody here. Up there. I've always determined right about hours where people start to that there. Okay, I'll finish before too long. I know we're scheduled for 2 hours, but 2 hours I can't keep your attention. That there. I'm sorry. I'm not that entertaining. That there. But I kind of determine all instructors can't keep your attention for 2 hours. I've talked to I asked a question, what do you do for 2 hours? And they said, well, we chit chat for an hour, we get this. So, yeah, you just waste time. That's it. So, all right, the special status word. That is a location in memory that contains the flags. The flags are important because they tell what's happening at there. So, when we look at this is a carry flag. That means that we've added two numbers and there's a carry out right there. This is an auxiliary carry. That means we carry from the third bit to the fourth bit. So if we add the number, say, 3E to 02, the answer is going to be 4, 1. We had a carry from the third bit to the fourth bit, right there. So that sets that flag. And that's important if we're going to be doing things like binary coding decimal. Because if we have a carry from the third bit to the fourth bit, it means we have to add 6 to it in order to make the number a legit BCD number, right there. So the user flag, that's one we can set. The register bank select right here, there, as I said, we're going to kind of get through that there, but those are when we can select registers there where we have multiple banks of registers to select right there. That gives us a little bit more room on our register selections because the original 808051 only had 8 registers. Now we've got 256 registers, and the way we do that is by we select different banks. Right there. Right there. The overflow means that we had an operation where we overflowed our 8 bits. The reserved means exactly that. We don't use that one. And the even parity bit, that's for error testing. If we read something, if we're going to be reading things out there, we set this. So these are the status bits. We don't often look at these bits individually, but there's instructions for those bits right there. And we looked at one already, and that was what? Jump not zero, or decrement jump not zero. That uses the 0 register, which is not part of this particular special function register, but there's another one further down. The carry flag does exactly that. It's dual purpose right there. And then we've got auxiliary carry flag. I mentioned that there. The user flag, right there, set bit. Overflow flag, even parity flag. And then we've got the B register. It's used for multiplying and dividing. That there. If we want to multiply 2 numbers, we have to use the instruction multiply AB. Right there. Now this particular processor only does integer multiplication. It does not do division per se. It does, but it's kind of funky the way it does it. Right there. The stack pointer, we'll talk more about the stack pointer. I think I've reached the point that I'm going to just kind of stop there. As I see people leaving for washrooms and I see people chit-chatting amongst themselves, I think we kind of reached the point that this is boring stuff, I know, right there. But what I like to do later this week is I'd like to come up with a little bit of a lab that I'm going to kind of go through a demo that's there. I went through one very simple one where I just added 3 numbers. I like some LEDs. But as we look at this particular textbook that we're looking at here, they get into the instruction set into the next chapter right here. Yeah, let's see, right here. Silicon Labs. This gets into the crossbar. I'm probably going to jump a little bit ahead into chapter 3 of this book. I'm going to use this book for a while. And has everyone found this on the e-learning site? Yeah, it's that there. And again, I'm trying to use books that I can find on e-learning just simply because it makes life easier. This particular book is completely open. You can share this, whatever. The publisher put it on the Silicon Labs site, and it's open for whatever that there. So it's copyrighted, but it's put out for public downloads that there. So there's nothing illegal about sharing this book with whomever that there. So that there. But we'll get into a little bit more detail. I think I'm going to stop at this point here. We're actually under an hour on a 2-hour class. I almost feel guilty here.